Now this question number 7, it's an interesting problem, and this problem was originally asked in Putnam 2000 exam. Let f be a polynomial with integer coefficients, and we have defined a1 as f0, a2 as f of a1, which is f of f0, and an as f of an minus 1 for all n greater than or equal to 3. Now we need to show that if there exists a natural number k greater than or equal to 3 such that ak is equal to 0, then we need to prove that either a1 is 0 or a2 is 0. So what we'll do is we'll assume a polynomial function. Let fx be some function, say b0 plus b1x plus b2x square plus bm x to the power m, where each of this bi is an integer. Now we'll consider this first case when a1 is 0, so it clearly means f0 is b0 and b0 is 0. Now if we'll take f of a1, so f of a1 will be again f0, which again will be 0. So in that case, all of them, a1 equals a2 equals a3 and ak, they are all 0. So it is a very trivial case. Now we'll come to the second case when suppose a1 is unequal to 0. Now in the question it says we have some number k greater than or equal to 3 such that ak is equal to 0. So ak, it is given that it is equal to 0. Now we'll take f of ak, then f of ak will be f0. Now f of ak is nothing but ak plus 1. So from here we'll write ak plus 1 is equal to f0, and f0 is nothing but it is a1. So ak plus 1 is equal to a1, and again if we'll take f here, we can write f of ak plus 1 is equal to f of a1, and f of a1 is nothing but a2. So from here we can write ak plus 2 is equal to a2. Now for polynomial functions with integral coefficients, we have this result that x minus y divides fx minus fy. So using this result, we can say that for any n, an minus 1 divides f of an minus f of an minus 1. Now f of an is an plus 1 and f of an minus 1 is an. So we can say an minus 1 divides an plus 1 minus an. Now we'll put the different values of n, then we can write a2 minus a1 divides a3 minus a2. Now we'll put n as 4, then we can write a4 minus a5, and we'll continue up to ak minus ak minus 1, and it divides ak plus 1 minus ak. We know that ak is 0 and ak plus 1, it is nothing but a1. So we can write a2 minus a1 divides a3 minus a2, a3 minus a2 divides a4 minus a5, and ak minus ak minus 1 divides a1. We can also say that a2, it is fa1 and fa1 is b0 b1 a1 b2 a1 square plus bm am square. Now b0 is nothing but a1, so we can write a2 minus a1 is b1 a1 b2 a1 square plus bm a1 square. It should be 1 here. So that means A1 divides A2 minus A1. So here we can also write that A1 divides A2 minus A1. Now A1 divides A2 minus A1, which divides A3 minus A2, which divides AK minus 1, which divides A1. So that means each of these factors, it should be either plus or minus A1. So from here we can write for any value of n, an minus an minus 1, it should be plus or minus a1. Now what we'll do is we'll write a1 minus 0 plus a2 minus a1 plus a3 minus a2 and then plus ak minus a k minus 1. Now in this question, this a1 will cancel, a2 will cancel, ak minus 1 will cancel. So here we'll get it as ak, and we know that ak is 0. Each of this factor, we know that it is equal to either plus a or minus a. So some of the factors must be plus a and some of the factors must be minus a, so that eventually they should cancel out to give us this result, which is 0. So of all these arrangements, which is a1 minus 0, a2 minus a1, a3 minus a2, a4 minus a3, and some random maybe a minus a t minus 1, and then a t plus 1 minus a t up to ak minus ak minus 1, there must exist a pair with alternate sign. So that means there must be at least one pair which will have one of the expression is positive and other expression is negative. Say this is suppose plus a and this is minus a, or this is minus a or plus a. So of all the expressions, at least two neighboring expressions will have different signs. From here we can write at minus a t minus 1 equals minus a t plus 1 minus a t. Now in this one at will cancel. So here we can say a t minus 1 must be equal to a t plus 1. So we get this result which says a t minus 1 must be equal to a t plus 1. Now we'll take functions. So we'll write f a t minus 1 equals f a t plus 1. So from here we'll say a t is equal to a t plus 2. So from induction we can say that this result is true for all the values of n. So in general we can say that an must be equal to an plus 2. Now if we'll put n as k, then we'll write ak equals ak plus 2, and we have shown that ak plus 2 is same as a2, and since it is given that ak is 0, so from here we'll say the value of a2 is 0. So any number k greater than or equal to 3, if ak is 0, it simply means either a1 is 0 or a2 is 0.